The hypothetico-deductive method is a common method of reasoning that's very important. It's a little different from our typical valid deductive arguments that we've considered, and it's also different from most of the inductive arguments that we've considered, primarily because of the context in which it's used and a couple other aspects of the method that are really important to learn. So the relevance of the hypothetico-deductive method is extremely significant because it is the central form of reasoning in the natural sciences. And it's not limited to any particular discipline. It's not limited to the natural sciences. It is common in history, philosophy, the social sciences. It can be modified a little bit to be used in just about any academic discipline. So it is an extremely important method of reasoning to learn. First, with the hypothetical part, we need hypotheses. And a hypothesis is a supposition used as a basis from which to draw conclusions. Now, that's extremely broad, and that's what allows disciplines in the humanities, for example, to use this hypothetico-deductive method. Another way of clarifying what a hypothesis is saying that it's any sentence that can be tested by checking the truth of predictions that follow from it. And again, the testing doesn't necessarily have to be empirical testing. It could be through thought experiments, for example. And this leaves things fairly wide open, but we are especially interested in hypotheses that may be proposed in the process of scientific inquiry. So we'll really focus in on the natural science use of the hypothetico-deductive method. Having said that, here are several examples of hypotheses. You can see that clearly some of these are very significant. It wasn't until the 1970s that we began to see that smoking causes lung cancer and have really good evidence for that. The Earth is spherical was actually something that was tested in various ways going back to Aristotle, but especially in the modern era after him. The Earth has been visited by intelligent extraterrestrials. Of course, that's one that some people believe is true and other people believe is false. It is testable. The speed of light is a constant, obviously an important fact in physics. A full moon causes an increase in accidents and violence, one that may not be true, but it could be investigated. Dinosaurs lived on the Earth 65 million years ago. Women are paid less than men for the same work, something to be explored in the social sciences. So these are examples of hypotheses that could be investigated through the hypothetico-deductive method. Now, as a very incomplete idea, we test hypotheses by deriving a prediction from the hypothesis and then investigating to see if the prediction is true. So that first part, whether you're in the natural sciences or any other discipline, you have to think through what possible consequences would be true if your hypothesis is true. And then you go out to see if those predictions are actually correct. Now, if the prediction is true, we would say that the hypothesis has been confirmed. Again, this is a very incomplete idea. And if the prediction is false, we say the hypothesis has been disconfirmed. But we need to be a little bit more careful about this. So let's consider some hypotheses and predictions, and let's make sure we're really clear on how this works. So when we say that a prediction is derived from the hypothesis, that means if the hypothesis is true, then the prediction is true. We can put this as a conditional statement, if H, then P. And we say that we investigate the truth of the prediction. Well, what are we doing? We're investigating whether or not P is in fact true. And if P is true, if we find the evidence that the prediction is in fact true, that gives us support for the hypothesis H. Now, if we were merely doing deductive reasoning, if H then P, P than H, obviously that is an invalid argument. That would be affirming the consequent, and that would be invalid. But this reasoning is not affirming the consequent. That's not what we're doing. We're not constructing a deductive argument. The context makes it clear that the argument is not deductive. But we do need a little bit more rationale to flesh out how exactly this works. One thing that we need to think about are auxiliary hypotheses. Auxiliary hypotheses are premises that are assumed to be true when the primary hypothesis is tested. So these are kind of background assumptions, and often these are left unstated, but sometimes they're relevant to consider. And they may include claims, for example, one, about the testing conditions themselves. You assume, for example, that your instrument is functioning properly or accurately, and you assume that whoever's doing the observation is able to report things accurately. So that would be some assumptions for just about any given test of an hypothesis. Another type of assumption is the background scientific knowledge that we have. So we have assumptions about commonly accepted scientific beliefs or relevant theoretical background knowledge that are significant for linking the hypothesis to the prediction. And so auxiliary hypotheses are important to consider. We also have some alternative hypotheses that are relevant, and these are other distinct separate hypotheses that have the same observational predictions as the hypothesis being tested. So we think, what else might be true? What other hypothesis might be true that would imply the truth of the prediction also? And alternative hypotheses then are going to be those that compete with the primary hypothesis, the one we're testing and investigating. And these are sometimes called then competing hypotheses because of this. So now we have two terms that are very important. Alternative hypotheses are the competitive hypothesis. Alternative hypotheses that would have the same prediction. Auxiliary hypotheses are those that are assumed to be true when we're doing our investigation of the hypothesis. Let's consider an example to show the relevance of alternative hypotheses, competing hypotheses. So we'll take this one from history and astronomy. Galileo proposed a test for the Copernican or heliocentric theory in favor of the Ptolemaic or geocentric theory. So Galileo wanted to show that the Earth actually revolves around the sun instead of the sun revolving around the Earth, which had been believed throughout the past prior to Galileo, prior to Copernicus, right around that time frame. And so he thought, well, if the Ptolemaic theory were correct, if in fact the sun revolved around the Earth, then Venus revolving around the Earth would only show a partial set of phases. It would never have a nearly complete set. But if the Copernican theory were true, we would have Venus between the Earth and the sun, both the Earth and Venus going around the sun, and there would be times when we have a nearly complete set of phases. So Venus would be like that of the moon. If we had a telescope, which were new, relatively speaking, at the time of Galileo, then we could watch Venus and see if it goes through a complete set of phases. And that's exactly what Galileo did to confirm the Copernican theory. A problem was that there were still people around who thought, well, hold on, maybe here's another way that things could be that would end up having the same prediction. The tectonic method, or the tectonic theory of the planets, had the idea that the sun revolves around the Earth still, but the other planets revolved around the sun, not Earth, right? So Earth then you have the sun revolving around the Earth, and then you have all the other planets, including Venus, of course, revolving around the sun. And if that were the case, that would predict that we would see a nearly complete set of phases in our observations of Venus, similar to those from the moon. So we would have the same results. So then you would have this, you had this competing theory to the Copernican heliocentric theory, the Tychonic theory. And fortunately, there were other possible ways of testing to distinguish between those two, so we quickly eliminated the Tychonic theory. But it was there as an alternative at the time. Okay, how does this work? How does the reasoning work when we have an argument for confirming an hypothesis? Well, first of all, you're only going to investigate hypotheses that are initially plausible. They have to have some degree of prior probability. Otherwise, it's no use making sense of trying to test hypotheses that are extremely low in probability. And then you have to have this linkage if the hypothesis and the auxiliary hypotheses are true. So we connect those, right? Then the observable prediction is true. If the hypothesis about the Earth revolving around the sun and Venus revolving around the sun is true, and we assume the telescope is we're able to see Venus clearly, we're assuming the grad assistant who would have to get up at night and watch Venus through the telescope is reporting accurately. I just their grad assistants have to do all the challenging work while Copernicus or Galileo or professors rest peacefully. Then if those things are true, the observable prediction is true. We go out, we investigate, we find that the observable prediction is true, and we don't have an alternative hypothesis with as high of a prior probability as the hypothesis we're initially investigating. Then if all those things are in place, we can conclude the hypothesis is true. So this is our argument form that we use whenever we're testing hypotheses. This is a little bit more complete example because we're including concerns about auxiliary hypotheses and alternative hypotheses. And one more other thing we should note, again, more clearly, this is an inductive argument, right? If all the four of those premises are true, the conclusion is probably true. So even though we have deductive in the method here, hypothetico-deductive method, the reasoning as a whole is actually inductive reasoning. Now that we've covered inductive versus deductive reasoning, you should be able to see that. Let's consider one more example. There is a sample argument for confirming an hypothesis that has to do with sunspots and radio reception. And so this is from the Science News, March 1931, a little bit more recent example from physics, where we were looking at sunspots. And it was noted that radio reception was noticeably impaired, coincidentally with the appearance of plentiful sunspots around March of 1931. And so previous to that rise of sunspots, radio reception was the strongest ever recorded. We were getting better and better at broadcasting and making radios to receive those broadcasts, and they were the best they had ever been. Sunspots are there, and then the reception is impaired. And so someone investigating this, Dr. Stetson, said that he expected the sunspots to decrease after about April 1st, so an astronomer would know the prevalence and phases of sunspots. And so he figured they were going to go away around April 1st. And then after that, radio reception will become as good or better than it was before the sunspot outbreak. And that's exactly what happened. The sunspots decreased after April 1st. Radio reception then improved. And so here's the reasoning process. If sunspots affect radio reception, then reception will improve after the sunspots diminish. The reception did improve after the sunspots decreased. And we conclude that the sunspots affected radio reception. Now, we didn't discuss possible alternative hypotheses there. There really weren't any known other reasons why the radio reception might have been diminished. So it wasn't clear what alternative possible alternative hypotheses there might be. Now, auxiliary hypotheses, again, are going to be about the telescopes functioning properly when we're looking at the sunspots, the reporting mechanisms, and all of those things we assume to be true. So we do have those. We didn't make those explicit, but they are always there. Anytime you're using the hypothetico-deductive method, you have to keep in mind the auxiliary hypotheses and the alternative hypotheses. But with those in mind, this is the kind of reasoning we have. If the hypothesis is true, then this prediction would be true. We investigate, we find the prediction to be true, and then we conclude that the hypothesis was true. And so this is the method of reasoning in the natural sciences, in other disciplines, extremely common and important to understand.